Boom! Yes, folks, how are you going? Hume here again. So in this video, we're going to talk about different types of numbers. All right, one of the things about understanding maths is that you have to understand that there are different types of numbers. All right, so we're looking at the types of numbers that are listed in the CSEC syllabus. You have natural numbers, you have whole numbers, you have integers, you have rational numbers, you have irrational numbers, you have real numbers. Those are the things that they have listed here for people who go in for the exam at the end of Form 5, the CSEC exam. But even beyond that, we have things like imaginary numbers. And then we have complex numbers, which is a combination of real and imaginary. But of course, that is something that is beyond CSEC, that you have to deal with that in Form 6. Right? That is Unit 2, if I'm not mistaken. Right, so let me start the discussion. And I'll draw in reference from the syllabus. And as we say in that, I want to encourage all of you all who doing the CSEC exam at whatever level, whether you're in Form 1 to 5 or whether you're a private student, get familiar with your syllabus. All right? Excuse. That is a big and very practical aspect of taking personal responsibility for your stuff. Don't sit and wait for your teacher, whoever he or she may be, to cover the syllabus with you. You could do that, but I just put in a notice, very often teachers teach based on their experience and based on the knowledge of the work, and sometimes they leave out certain things in the syllabus. And then you go in the exam and you see something come up, boop, that wasn't on the past papers that the teacher didn't cover, but it's right there in the syllabus. So I'm giving a fair warning to everybody. Use your syllabus. We're in 2022. You don't have to jump through the kind of hoops that you had to jump through back when I was doing CXC. In the 90s, it's online, it's on the internet, and you don't even have to pay for it. Use the technology now. Use the people technology to help yourself. Right, so back to the discussion. So we start off with natural numbers. And taking the approach of just talking about it, you are free, as always, to go and check your stuff on Google and whatnot. So a natural number is a number that we could physically count. We could physically see. Right? Natural numbers would be the set of positive numbers. So natural numbers would be like 1, 2, 3, 4 going up the road. So if you're in a car park and you see 5 cars, you could count 5 cars. That is a natural thing. You have 5 fingers on each hand. That is as natural as you could get. 5 fingers, 5 toes on each foot. 10 toes, 10 fingers. That is something that you could physically count. So that is where we start. All counting from whenever, since Adam was a boy, as we like to say, would have begun with natural numbers. Things that you could actually count. And then as time progressed, humans would have developed different number systems, other types of numbers, to cover other types of circumstances and situations that may have been a little beyond the natural numbers. So for example, we have, let me see, integers. Right? We have integers, which will be whole numbers again, stuff that you could count. So in other words, we're not dividing anything as yet. We're just dealing with 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Right? Natural 5 is you could count 5 cars in a car park. What is the meaning of minus 5 if we're talking positive and negative? Right? So the negative sign now enters the picture somewhere in the history of mankind. The idea of negative, the idea of taking away, the idea of what does that mean? Right? The negative sign is not a natural thing. In other words, you can't count minus 5 cars. You can't count minus $5. You can't hold minus $5 in your hand. You could hold 5 singles in your hand. That is natural. You could see it, you could feel it. You could even smell it. New money now. You know the smell of new money, we like to talk about that. You mightn't see minus $5 in your hand, but you could feel it in your pocket, in the sense that if you lose $5 or if you owe somebody $5, you know exactly what that means. So in terms of money, the negative sign can be used to denote something like you're owing people and that kind of thing. So the negative sign has a specific meaning in different contexts in mathematics. And that is basically what it is. So the negative sign does not point towards natural numbers. You can't count a negative quantity physically. Naturally, if we could say that. But depending on the circumstance that you're in, the negative number has a particular meaning, and it is your responsibility to know what the negative number means in every circumstance that you're dealing with. So another example, let me say measuring height. If you're going up, that's positive, and if you're going down, you could count that as negative. So in other words, if we take a geographical approach now, you know we have sea level. Sea level is normally measured as the zero, as the base. Zero is a whole discussion by itself. We might just touch on it in this video, but maybe at another point we will deal with that in some more detail. So you start from 0 and you go up. So 5 meters up is plus 5 meters. Minus 5 means that you're measuring down. You're measuring below sea level. So in the case where you're measuring up and down, the negative sign simply means that you're measuring down as opposed to up. Right? So I want you to understand that the negative sign means something. And as you get deeper into the maths, you will find that it means different things in different scenarios. We're not going to deal with that today. All right? So in discussing negative numbers and natural numbers, by default, we also would have discussed whole numbers and integers. Now, the whole numbers, here is where we had to pause a little bit now. The whole numbers also include 0. So in other words, 0 is not a natural number. You can't count 0. You can't hold 0 in your hand. 0 is nothing. 0 is something that we use in mathematics to represent the whole idea of nothing. So if you have no cars in the car park, that's 0 cars. If you have no money in your pocket, that is $0. If you're at sea level, so you're neither up or down, your height is measured at 0 meters. So again, the 0, just like the negative sign, could have different meanings in different contexts. And that is something that you also have to be aware of. So in the same way that you have to be aware of what the negative sign means, depending on the context that you're operating in, it is the same way that you have to be aware of what the 0, what the idea of 0 means in different contexts. Right? I like to use money as an example because I have seen time and time again teaching people a particular topic, and you're explaining and you're thinking and they're not getting it at all. And as soon as I decide to use money as an example, as an analogy, and boom, everybody understands automatically. Why? Because money is something that we're dealing with every day. We're using money. Money is central to almost everything that we do. So I like to use money as an example, as an analogy to explain certain concepts to people. Right? So we talk about natural numbers, things that you could feel, you could hold, you could touch. In other words, natural numbers, and here's where I am improvising now, right? Natural numbers would be the case where you could actually apply your physical senses to it. right? Think about it. You could see 5 cars, you could touch 5 cars, you could taste 5 current souls. What's the other senses? Whatever. You could apply your physical senses, your physicality, to the whole idea of determining how much of whatever it is. You could do that with natural numbers. 0, on the other hand, is not natural. We could say that too if we want. 0 is not natural. It's not natural. 0 just means that you have nothing. Whatever it is you're measuring, you have nothing. And the physical symbol 0 is what we use to denote nothing. 0 is included as a whole number, but it is not a natural number. So I'm spending all this time explaining these things because we want to start at the starting line. We want to get a little appreciation of numbers, different types of numbers, and then we move on from there. Your integers now is where you go beyond just the whole numbers and the natural numbers, and you include negative numbers. So you could have a positive integer, you could have a negative integer, and you could also have 0. So 0 is also included in the set of numbers that we refer to as integers. So just remember, natural numbers would be a regular counting. 1, 2, 3, 4, going down there. Again, think of how we learn to count. When we learn to count as children, when we're teaching our children to count, we don't start from 0. We start from 1. We don't say 0 fingers, 1 fingers, 2 fingers, 3 fingers. We start from 1. So in other words, it's something that we could do naturally as a normal course of enterprise. You start to count from 1, 2, 3, 4, going down the road. And then you start to expand. Whole numbers, you include the 0. So you move from natural numbers to whole numbers, and then from whole numbers, you move to integers by moving beyond the 0, and you now adding the negative numbers. All right? So if I can draw a quick diagram, let me see. Your natural numbers would be 1, 2, 3, 4, ... going down the road. That's your natural numbers. And then we change the color and we add a 0. 0, 1, 2, 3, 4, going down the road. That is your whole numbers. And then we go a little further now. We add negative numbers. Right? Minus 1, minus 2, minus 3, Right? So these in red here would be your integers. These would be your whole numbers. These would be your natural numbers. Right? So this is something that you could see visually for those of us who like to see. Visualize. Nice. Now is where we're going to get a little more. Now, we could deal with the real numbers afterwards, because all the numbers we would describe here would fall under real numbers. Let me say that again. All the different classes of numbers that we would deal with here for the purposes of people who do an exam, CXC, CSEC, would fall under real numbers. So at this level, you don't have the headache of distinguishing between a real number and an imaginary number. You don't have the headache of distinguishing between a real number and a complex number. Complex is real plus imaginary. Right? Just like a lot of things in life. You take the real thing and you take the imaginary thing, and when they come together, it's complex. Or as we like to say in Facebook language, it's complicated. Alright? So don't worry about that. Anything that is not real, that is beyond form 5. Everything we're talking about here will fall under real. So these are what we would call subsets of the entire set of real numbers. We will deal with the details of sets and subsets and the notation, and we will use these same examples in a subsequent video not too long from now. All right. So let us now go to a different category of numbers. We have rational numbers and we have irrational numbers. All right. So let me slow down. Let me slow down the movement a little bit now. Let me start by talking about rational numbers. The word rational to describe rational numbers comes from the idea of a ratio. Right? So ratio is the noun, rational is the adjective. See? We're getting into language now. So the noun is ratio, the adjective is rational. So in other words, a rational number is a number that can be expressed as a ratio. All right? It's not as complicated as you think it is. All right? A ratio, without going into the other details of it, no. We will deal with that later when we start to talk about ratio in a separate video. A ratio is simply something divided by something. Is a ratio. So 1 over 2 is a ratio. 3 over 5 is a ratio. 4 over 7 is a ratio. 7 over 9 is a ratio. These are the ratios that we commonly refer to as fractions. So now is not too early to understand the connection between the ratio and the fraction. Right? For the purpose of simplicity, you could simply say that a ratio is a fraction. You could also say that a fraction is a ratio. Right? Again, I just give you a little one-liner there to stick in your back pocket. You'll need it later. Yes? So you have different types of ratios. You have the ratio where you see, we had to use the language interchangeably, so to speak. You have the ratio where the number on top is smaller than the number on the bottom. We know that the number on top is the numerator, the number on top is the denominator. Again, we're talking about ratio as a fraction. So that would be a proper fraction. And then you have the improper fraction where the number on top is bigger than the number below. Right? I think that is what I said just now. So 3 over 5, proper fraction. 5 over 3, improper fraction. We would have been exposed to this at some level. Most of the people who see in this video, most of you would have been exposed to this. Proper fractions and improper fractions. What to do with it and how to do it is a different matter altogether. Because we know a lot of people still need to get the whole idea of manipulating fractions down. That is one of the big topics in maths. But we come into that eventually too. Alright? So, proper, improper, rational. This is a ratio, this is a ratio. Right? But we have different types of ratios. We have ratios that are rational, and then we have ratios that are irrational. Now again, this is where the topics start to cross into one another. Because without too much of a knowledge of the numbers, you wouldn't be able to look at a fraction and tell whether it is rational or irrational. You wouldn't be able to do that. The ability to do that enters the picture when we start talking about decimals, which we know is simply another way of writing fractions. That's all. That is all. And again, I'm just saying that for the purpose of simplicity. We will get into that in more detail at a later date. So for example, let me go with the examples now. If we say that we have a fraction, which is a ratio, which is a rational number, 1 over 2. 1 over 2. As a decimal, we know that that is 0.5. Everybody know that half is 0.5. We know that. No, not everybody know that 3 over 8 is 0.375. But we'll deal with that in another video too. Right? 1 over 2 is 0.5. So we starting at the point that everybody familiar with. So we know this. 1 over 2 is a fraction that is 0.5 as a decimal. Both of these represent the same quantity, the same number written in a different form. Both of these are examples of rational numbers. What happens now if we say we move from 1 over 2 to 1 over 3? Aha! Different kettle of fish we're talking about here now. Because 1 over 3 would be 0.3333333 going down the road. Right? This is what most of us would have been exposed to as a recurring decimal. Alright? So once the decimal doesn't stop, then we refer to it as an irrational number. So in other words, it is an irrational ratio. It's a ratio, you know. And it's rational, but it's irrational because it don't know when to stop. You know? Like how some of us humans could be sometimes. Think about when you describe somebody as being an irrational person. One of the characteristics that most irrational people have in common is that they don't know when to stop. And the thing that they don't know when to stop is usually some kind of behavior or behavioral pattern that we're not too comfortable with. So in other words, sometimes people know when to stop certain things. And then sometimes people don't know when to stop. So if you're having difficulty remembering the difference between a rational number and an irrational number, think about the whole idea of the number coming to a stop. The decimal expression of the number coming to a stop. Right? So anytime you write a rational number, anytime you write a ratio and you transform the ratio to a decimal and the decimal is stopping at all, then that is an irrational number. Now, let me tell you a secret. Whole numbers are also rational numbers. Reason being, every whole number that you could think of could be written as the number divided by 1 and therefore as a ratio. So in other words, if we have the number 6, then 6 could be written as 6 over 1. If you have the number 22, 22 is 22 over 1. If you have the number 385, then 385 could be written as 385 over 1. So you have to understand that even whole numbers come under the category of rational numbers because you could express it as the number itself divided by 1, which is a very important technique in mathematics. There are many cases and situations where the simple ability to express a whole number as a ratio. You have 7, you put it as 7 over 1. You have minus 3, you put it as minus 3 over 1. That ability will pull you out of certain kinds of situations when you're dealing with certain kinds of topics in maths. Most commonly used when you're dealing with fractions. When you're dealing with fractions, the ability to express a whole number as a ratio is one of the most fundamental techniques that you could employ but we will deal with that later. So you might have 7. 7 is 7 over 1. You could also express 7 as 14 over 2, or 21 over 3, or 28 over 4, or let me see, 84 over 14. 84 over 14. 14 by 7 is how much? 14 by 7, 7 4 is a yes. No? Hold on. 14 by 7 is equal to 98. 84 by 6. 84 divided by 6 is 14. Let's get my tables mixed up now. We could do a whole video and we'll discuss the importance of your tables afterwards, right? But yes, so 98 over 14 is 7. So 7 is now 98 over 14. So the ability to express a whole number as a ratio is very important. I'm spending plenty time talking here. But if you listen to what I'm saying, you'll pick up certain things that will either stick with you or that you could go and investigate on your own. Alright? So, bottom line, a whole number could be also expressed as a ratio. A whole number is a rational number. Now, we use proper fractions here, which means that when you express it as a decimal, it will be 0 point something. But if it was, let me say, instead of 1 over 3, if it was 5 over 3. Alright? 5 over 3 is what as a decimal? I'll pull the calculator here. 5 divided by 3 is equal to 1.666666 going on the road. Again, right? It shows no sign of stopping. So as much space as we have on the board, we will use to express the decimal. And we put 7 at the end. If the board was wider, we'd still be going with 6s. Right? So whether the fraction is proper or not, if the decimal is never ending, then it still is an irrational number. So 2/3 as a decimal would be 0.666666666666666 going down the road. Proper fraction, ratio, irrational number. Improper fraction, ratio, irrational number. Proper fraction, ratio, rational number. And then of course, look the thing, okay, we'll come back at that. If we have 12 over 2, that is an improper fraction, that is equal to 6. If we have, let me say, 7 over 5, that is 1 and 2 over 5, that's 1.4 as a decimal, right? Improper fraction can be expressed as a whole number, rational number. Improper fraction, decimal, but the decimal has an end. If decimal stops, we could refer to it as a finite decimal if we want, because it has an actual end, 1.4, as opposed to these fellas here, which we can refer to as infinite decimals. It just goes on and on for as long as you care to go until you're tired and you stop. 1.4, rational number. Alright? So some common examples of irrational numbers that we are aware of would be your pi. Right? We know that pi is, and again, I'm just giving the ratio without going into all the details. We know that the ratio pi is given as 22 over 7. That is the ratio that is equal to pi. Right? 22 over 7 is equal to pi. As a decimal, that is equal to, let me see what we have here, boy. Pi. Hold on. Pi and my calculator. Pi, where are you? It never takes long to find my pi button yet, you know. Okay, here what we could do. We could just divide 22 by 7. 22 divided by 7 equal, boom, 3.142. Right? 3.142 8 5 7 1 4 2, and the pattern repeats. So I think how it happens is that, if I'm not mistaken, right, this may be subject to correction. I think this pattern here is a repeating pattern. So 1 4 2 8 5 7 1 4. My calculator stops here at 3, but it goes back to now 1 4 2 8 5 7 going down the road. Something along that lines, but it just goes on and on. Pi is an excellent example of an irrational number. Another example, which I will give, but again, with the caveat that this number is way beyond what you will be dealing with at this stage. I don't even know. Yes, I think they deal with this in Form 6. Number E. I'm not sure what is the physical ratio for E, but E is equal to what? Yeah, let's check my mic there. E is equal to, let me see, Shift E to the power 1. E is 2.718 281828 going down the road. And I think it's the same thing as pi, that is subject to correction. There are other examples, I am sure, but these are some common examples of irrational numbers. This, don't hurt your head about that. You wouldn't need that anytime soon if you're below the level of Form 5. Pi, yes, you definitely will be interacting with pi, because once you talk in circle, you're talking pi. Alright? So pi is an excellent example of an irrational number. We dealt with some examples here. So let me give you another secret now. Alright? Generally speaking, I'm being very careful here now. Generally speaking, anytime you have a ratio where you have an odd number, you would normally have an irrational number. The decimal that you get when you divide by an odd number is usually an infinite decimal, which means that you will ultimately end up with an irrational number. The number 5, however, is a notable exception. You divide by 5, you will get a finite decimal. 1 divided by 5 is 0.2. 3 divided by 5 is 0.6. 12 divided by 5 is 2.4. 50 divided by 5 is 10, etc., etc., etc. Right? So 5 is an exception to that general trend. Generally, when you divide by prime numbers, you also end up with irrational numbers. We will deal with prime numbers in the next video following this. I don't want to put too much in one space at a time. Alright? So we have prime numbers. We also have another category of numbers. These are numbers that we refer to as perfect squares. Right? Squares and their square roots. We will deal with that in the next video too. The video that following from this one. So just to wrap up this particular video, quick summary. Yes, we dealt with different types of numbers. We started off by discussing natural numbers, then we went to whole numbers, and then we expanded that to integers. We spoke about rational numbers, rational being derived from the whole concept of a ratio. Ratio, of course, being the same thing as a fraction, which you could then express as a decimal. And the decimal form of the number is what will give you very quickly a visual answer to the question of whether the number is rational or irrational. As soon as you see the decimal, you know whether the number is rational or irrational. If the decimal is finite, it stops after 1 decimal place or 2 decimal places or 3 decimal places or however many. It doesn't matter however many. If it stops, then it is a finite number. Finite decimal, sorry, which means that you're basically dealing with a rational number. A finite ratio, so to speak. So in other words, let me write the thing down now, man. Alright? So you have two terms, again, two terms that I want you to get familiar with. You see how much vocabulary we have in this maths? Right? You have what we refer to as a finite ratio. Ooh, pressure boy. Right? A finite ratio. That is a ratio which, when I express it as a decimal, it is finite, as the word implies. It stops after however many decimal places. And then, in opposition to that, you have the infinite ratio. Right? Infinite ratio, which is you divide and you get a decimal, and you find that the decimal is infinite. It just goes on and on and on. This is what will give you your irrational number. This will give you your rational number. So your finite ratio will give you your rational number. You see how much times I'm repeating myself, eh? Right? And your infinite ratio is what will give you your irrational number. Yeah? Irrational number. Right. And then we looked at specific examples. We dealt with the fractions, the improper fractions, and the proper fractions. We mentioned pi and e as two what we refer to as naturally occurring numbers. Right? I'll probably find another video that discusses that. Naturally occurring numbers. Pi is the ratio of the circumference to the diameter. We will deal with that in some more detail later. That ratio in any circle is the same, 22/7, 3 point, whatever. Irrational number. E, 2.71 is going on the road, irrational number, you don't need to worry about this now. We also mentioned that your whole number could also be expressed as a rational number. And then we talk about different denominators that give rise to your finite and your infinite ratios. All right? So when you divide by certain types of numbers, you get your infinite ratio. And then, of course, we're dealing with perfect squares and numbers that are not perfect squares, which will then bring into question the whole idea of the square root. That, too, is connected to your irrational and your irrational numbers. But we will discuss that in another video. So stay tuned. We have plenty more things coming up.